Hi, I'm Sandy Ghai, Product Manager for AlloyDB.
And I'm Abhinav Khushraj, Product Manager for BigQuery.
Today, we're going to be talking about how databases can help you more easily add ML to your applications. We see a lot of app developers looking to build better experiences using machine learning. Whether that's a mobile app developer looking to use AI ML to optimize a customer journey, to a retailer looking to offer the right product to the right customer, or a financial services user looking to detect fraud within a transaction. There are so many opportunities to build more personal, more intelligent experiences in your applications.
But you know, Sandy, while people see a lot of promise in what AI and ML can do for their business, they are struggling to operationalize AI initiatives. You know what happens typically? Typically, enterprises will spend a lot of time and energy to build data pipelines to bring data into a warehouse. They'll build governance models around it, and so on. However, when they want to do an ML project, they have to take the data out again. Not only do they have to build and maintain new pipelines to export the data, it often results in loss of governance and can lead to security issues. And finally, there's the headache of figuring out and maintaining infrastructure, both for training and inference. Either they underserve, creating a bad experience, or overserve, resulting in huge costs. So the traditional approach results in skill gaps, significant cost and complexity, and can lead to security issues.
And that means fewer customers actually integrate machine learning into their apps. I think we can both agree that there's a better way.
Absolutely, let's show them.
Chances are you are already using a database to back your application and a data warehouse for analytics. Today, Abhinav and I are going to talk you through a demo on how you can use your existing stack to build models and integrate them with your apps without having to move data around.
You can even use your existing SQL skills to both train models and deploy them in your applications.
There are a few products that make this super easy. Today, we're going to talk about AlloyDB and BigQuery. AlloyDB is a fully Postgres-compatible database engine with superior performance, availability, and scale. It's great for demanding workloads. It's 4 times faster than standard Postgres for transactional workloads. But it also allows you to unify analytical workloads and generate more real-time insights on your data. But one of my favorite things about AlloyDB is its native integration with Vertex AI. With AlloyDB, you can call a model in Vertex AI directly from the database, enabling high throughput, low latency, augmented transactions. One of the examples we're going to talk about today is a fraud detection use case. AlloyDB can call a fraud detection model within a transaction. So if John Doe tries to make a purchase for $20, we can call Vertex AI using this ML predict function and determine if it's fraudulent as we save it down. This feature is actually also available in Cloud Spanner, which is GCP's relational database offering with unlimited scale, strong consistency, and up to 5 nines of availability.
BigQuery is an industry-leading cloud data warehouse processing 110 terabytes of data every single second. It has a serverless design. Users don't have to worry about managing scale. Whether you have just a few hundred rows or billions of rows, BigQuery automatically scales up or down to manage it. And it is unique in the industry to have built-in capability for doing ML with BigQuery ML. By being right inside the database, it removes the need to manage data, and BigQuery manages all the training and serving infrastructure. Enterprises large and small have trained millions of models using BigQuery ML for a variety of use cases ranging from forecasting, customer segmentation, or anomaly detection. In fact, its usage grew by over 200% in 2022. BigQuery ML brings BigQuery and Vertex together to create a simplified data to AI journey. It integrates with Vertex in many different ways. Users can train models for BigQuery leveraging Vertex's training infrastructure, or users can write a few lines of SQL code to run inference against Google's state-of-the-art pre-trained models for images, natural language, or translation. And finally, for enterprise users, it provides a seamless MLOps experience for managing models, building a feature store, and more.
What's so cool about these products is that they make it easy to integrate ML into your existing apps. Today, we're going to walk through a fraud detection use case. First, let's start with the existing application. You are already using AlloyDB as your database and storing your retail transactions there. You might also have a database pipeline using DataStream that is replicating data to BigQuery for offline analytics, and maybe even a Looker dashboard for reporting. Now, we'd like to start incorporating ML to predict whether our retail transactions are fraudulent. We can use Vertex AI, GCP's AI and ML platform, to build, deploy, and scale machine learning models faster with fully managed ML tools for any use case. This integrates nicely with both BigQuery and AlloyDB. So first, we need to train our model. For data scientists who want full control, Vertex AI offers custom training. But for the many users who don't have data science expertise or who want to speed up time to market, BigQuery ML can help you train a model super quickly, and all you need is SQL.
Users write a simple SQL query with a create model statement specifying the model type and the training data set that is inside BigQuery. And then, in addition to that, during model creation, users specify an option to register the model with Vertex AI's model registry. Now, this makes it super easy for enterprises to have a single place to manage all their models. And once the model is registered, users can go to Vertex AI to create a prediction endpoint and deploy the model for online serving using Vertex AI prediction while specifying the serving infrastructure that they like. It's that easy, Sandy.
So now we've trained our model and registered an endpoint. Let's talk about inference. How do we actually integrate those predictions into our apps? Again, AlloyDB makes that easy because you can call your Vertex AI endpoint from the database itself. I'm turning it over to Gabe Weiss to show you how this works.
We're going to walk through how you can invoke predictions on Vertex AI endpoints from AlloyDB using SQL. This is functionality AlloyDB provides so that users don't have to manually build a custom integration for machine learning. Here's our project where an AlloyDB cluster has been created, and we will be using the primary instance in this cluster to invoke predictions. First, we need to grant this AlloyDB cluster permissions to access Vertex AI. To grant those permissions, we need the project number. To find it, navigate to the project dashboard, and project number should be listed under project info. We're using a separate project for our Vertex AI endpoints. As you can see, we have a fraud detection endpoint deployed here already. Instructions to train and deploy this model will be linked in the description below. To grant permissions, go to the IAM page of the same project and click on Add. Paste the principal in the format mentioned in the documentation, and change the project number to the value we got from our AlloyDB project. Choose the Vertex AI user role so that AlloyDB clusters in that project can invoke predictions on Vertex AI. And finally, click Save. As we can see, the principal has been granted the necessary permissions, and now AlloyDB instances should be able to access Vertex AI endpoints. Note, in some scenarios, users might have to check the Include Google Provided Role Grants box to view the principal we just added in this list. Now, to finally invoke predictions on the endpoints, we need some details. Navigate back to the Vertex AI endpoints page. In this case, we want to invoke predictions on the fraud detection endpoint. Click on the sample request link. Take note of the endpoint ID and project ID. Also, note the region in which this endpoint is deployed. In this case, it's US Central 1. Now, the final step is to invoke predictions on this endpoint using SQL. We will connect to the AlloyDB's primary instance from a client VM in the AlloyDB project. We are using the PG CLI client, which is a wrapper over PSQL to connect to the fraud database. Let's create a table fraud detection data, which will contain transactions over which prediction will be invoked to determine whether a particular transaction is fraudulent or not. For demonstration purposes, we'll load data from a CSV file into this table. Let's look at some rows in this table. Some of our data has been transformed to protect user identities and sensitive features. That's why we see the data in this form and columns named as V1, V2, etc. And some columns have been preserved as is, like time and amount. To invoke predictions, we'll be using a function named MLPredictRow. This function is provided by the Google Vertex AI extension for AlloyDB. To use it, we need to install the extension first using the create extension command. Now that the extension is installed, let's start with a query which runs predictions on some rows of our fraud detection data table. For each row, MLPredictRow will be called with relevant arguments. The first argument of the MLPredictRow function is the endpoint, and we plugged in project ID, region, and endpoint ID into this format, which we got earlier from the sample request. The second argument is a JSON object with an instances key containing the actual data that we want to get the prediction scores for. We want to get individual prediction scores for each row, which is why row to JSON here is converting a row in the table to JSON. The response JSON object returned by Vertex will contain prediction scores in the predictions key. So here you see we're extracting data from the predictions key using this operator. Finally, we're limiting the number of rows to 500 just for demonstration purposes. Now let's execute our query. The response will take a little time, so we're speeding up a bit here to get to the good stuff. This is the response returned by the query. We have a time column that is directly projected from the table, and fraud score column, which contains the prediction results. Class 0 here means the transaction is non-fraudulent, and class 1 means that the transaction is fraudulent. So for the first row, the prediction score corresponding to class 0 is 0.99, which is significantly higher than the score corresponding to class 1, meaning the model has predicted that this transaction is non-fraudulent. However, looking at our second row, the score corresponding to class 0 is only 0.1, which is significantly lower than the score corresponding to class 1, meaning the model predicted that this transaction is fraudulent. This query took around 14.5 seconds to execute, because we're sending only one row to each request for Vertex AI, as in 500 requests just got sent to Vertex AI to get predictions for the 500 rows. To improve throughput, we can send multiple rows in a single request to Vertex AI. Our next query will do exactly that. We're going to use group by clause to batch multiple rows together. Just to demonstrate, we're going to group on a random integer ranging from 0 to 4, meaning there can be at most 5 groups or batches. And since we're invoking predictions on 500 rows, the expected batch size would be about 100. Now the data under the instances key will be a list of JSON objects instead of a single JSON object like the previous query. We generate this list using the JSON_ag function. Finally, we also then need to unpack the aggregated rows into individual rows. Unnest and JSON array elements functions are responsible for doing that work. Now let's run the query. We roughly see around a 21 times improvement, even though both the queries are invoking predictions on the same sets of rows. So just by batching, we can get significant performance improvements. The amount of performance improvement will obviously vary from case to case and depends on factors like network latency, batch size, number of parallel workers used by the queries, etc. Thanks for watching.
Wow, that was pretty cool and super easy, Sandy.
Thanks. So now we've trained our model and deployed it into our application. We didn't need to move data around or host or manage any additional resources. We also didn't need any specific data science skills. We were able to run and train our predictions using just SQL.
Thanks so much for tuning in. To learn more about using AlloyDB and BigQuery to integrate machine learning into your applications, check out the description below.